In this chapter, we focus on discrete probability distributions, and this lesson will cover the basics of probability distribution. This chapter combines the methods of descriptive statistics presented in chapters 2 and 3 and those of probability presented in chapter 4 to describe and analyze probability distributions. Probability distributions describe what will probably happen instead of what actually did happen, and they are often given in the format of a graph, table, or formula. In order to fully understand probability distributions, we must understand the concept of a random variable and be able to distinguish between discrete and continuous random variables. In this chapter, we focus on discrete probability distributions. In particular, we discuss binomial probability distributions. In this chapter, we will construct probability distributions by presenting possible outcomes along with the relative frequencies that we expect. So in the situation where we want to find the numbers of girls for couples that have 2 children, in chapters 2 and 3, we would collect sample data from families with 2 children and then find statistics and create graphs. So we could set up a table where X represents the number of girls in the families, and we could have 0 girls, 1 girls, or 2, and F represents the frequency of families with those numbers of births. X bar is the mean, S is the sample standard deviation. From chapter 4, we could find the probability for each possible number of girls. So the probability of having 0 girls is 0.25. Probability of 1 girl is 0.5. Probability of 2 girls is 0.25. So we can combine these concepts in chapter 5, where we can create a theoretical model of expected results, and then we can find the parameters. So the expected results for numbers of girls for couples having 2 children is we could have 0, 1, or 2 girls. These are the expected results, and this would be the mean and the standard deviation. This section introduces the important concept of a probability distribution, which gives the probability for each value of a variable that is determined by chance. So we will have to give consideration to distinguishing between outcomes that are likely to occur by chance and outcomes that are unusual, in the sense that they are not likely to occur by chance. A random variable is a variable typically represented by X that has a single numerical value determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value of the random variable, often expressed in the format of a graph, table, or formula. A discrete random variable is either a finite number of values or countable number of values, where countable refers to the fact that there might be infinitely many values, but that they result from a counting process. A continuous random variable has infinitely many values, and those values can be associated with measurements on a continuous scale without gaps or interruptions. So a discrete random variable has to be countable. It can't be split up into decimals, but a continuous random variable is associated with measurements. So anytime we're measuring something, that would be a continuous value. So let's practice identifying if the given random variable is discrete or continuous. The cost of conducting a genetics experiment. Cost is actually continuous because when we measure cost, it's actually in a decimal. Like usually we say $1.99, but if you notice when you go to gas stations, they always have a third decimal up here. So you can measure price to an infinite amount. So it is a continuous variable. The number of supermodels who ate pizza yesterday. People are countable, so that would be discrete. The exact lifespan of a kitten. So lifespan can be measured with increased precision on a continuous scale, so this is continuous data. The number of statistics professors who read a newspaper each day. So this value is countable. You can't split it up into decimals or fractions, so that would be discrete. The weight of a feather. Weight is measured, and so that would be continuous because you can measure it with a continuous scale of precision. So here are the requirements for a probability distribution. There is a numerical random variable x, and its values are associated with corresponding probabilities. So when we set this up, we have a table generally where we have x, and x has to be numerical. So we can't have categories here for x. You can have numbers associated with x. The second part of the table is p of x, or the probability of x happening. So a probability distribution, the sum of all those probabilities must be 1. So when we see this Greek letter sigma, sigma represents the sum. After it, it tells you what you're adding up. So the sum of p of x must be 1. So when I add up all of my probabilities, it needs to be 1. Now many times because of rounding errors, you're going to have decimals here. And so as long as it's very close to 1, like 0.999, that's okay. But if you add up and you get like 0.997, no. Each probability value must be between 0 and 1 inclusive. So the individual probabilities have to range from 0 to 1. So they're in decimal form like 0.3 or 0.5. So you can't ever have anything greater than 1 or negative in those probabilities. A probability histogram is similar to a relative frequency histogram, but instead the vertical scale shows the probabilities. So some formulas that we'll need to know for this chapter: the mean of a probability distribution. So if x is the value of the random variable and p of x is the probability of that value of the random variable, so you'll have different values for x, you'll have probabilities. Remember that the sum of the probabilities must be 1. So when we have this probability distribution, to find the mean is equal to the sum of x times p of x. So this symbol right here stands for the mean, and it's actually population mean. Sigma represents sum of something after it tells you what to add up. So here's a little formula. I have to take my x's, multiply by the probabilities p of x, and then I add that up. So when I have a probability distribution, I'm going to have another column here where I'm going to multiply straight across. 0 times 0.25, 1 times 0.25, 2 times 0.25, and I add that up, and that gives me the mean. The standard deviation of a probability distribution. So the symbol for the standard deviation is sigma. This is the population standard deviation. So sigma, or the standard deviation, is equal to the square root of the sum. Now here notice it's a little different. We want to multiply the squared x's times the probabilities. So we have to square the x's. So 0 squared is 0, 1 squared is 1, 2 squared is 4. And we keep our original probabilities. We do not square those. And then we multiply the squared values times the probabilities. Then we add that column up. So that answer goes here, and then we subtract the square of the mean. So whatever answer I get from here, I'm going to square it, subtract that from the sum here, and then I take the square root of that final answer. The expected value, E, of a probability distribution is equal to the mean. So here's an example of a probability distribution, and we first want to determine if it is going to meet the requirements of a probability distribution. So x represents the values, and over here p of x is the probability of that x occurring. So these are the different probabilities associated with those values. So we first need to add the probabilities together. So the sum of the probabilities is 0.977. So this is not a probability distribution because the sum of p of x must equal 1, or 0.999, which would round up to 1. The following table is a probability distribution that's set up for the number of girls in 2 births, and so we want to find the mean and the standard deviation for this. Okay, so notice that we have first we do the x times p of x. I'm going to go back and show those steps and then you can see the answers. So in order to find the mean, the formula for mean is it's the sum of x times p of x. So first let's see if this is a probability distribution. So if I add the probabilities 0.25, 0.5, and 0.25, the sum of the probabilities is 1. So it does satisfy that requirement. Now I want to multiply the x's times p of x. So 0 times 0.25 is 0, 1 times 0.5 is 0.5, and 2 times 0.25 is 0.5. So when I add that together, I get 1. So the mean is mu, and that is equal to 1. The standard deviation formula for that is it's the square root of the sum of x squared times p of x minus the square of the mean. So I need to first determine the x squared times p of x answers. So x squared, if I go back over here, 0 squared is 0, 1 times 1 is 1, and 2 times 2 is 4. Now I'm going to multiply these numbers by the probabilities. So I get 0 times 0.25 is 0, 1 times 0.5 is 0.5, and 4 times 0.25 is 1. So when I add that column together, I get 1.50. So the standard deviation is the square root of that sum, 1.50, minus the mean squared. So the mean was 1, and I want to square that. So in my calculator, I'm going to first get that square root on my calculator. So I'm going to do second, and then I'm going to hit that x squared button because above it is the radical. So then it comes up like that, and I'm going to type 1.5 minus 1, and then I'm going to hit my x squared button to make it square, and then I press equals. So that answer is 0.71. That's the standard deviation. Okay, so let's determine if a probability distribution is given. If it is, find the mean and standard deviation of the probability distribution. So we first want to make sure that the sum of the probabilities is going to be 1. So when I add up the probabilities, it does equal 1. So it is a probability distribution. So now let's find the mean. So the mean is the sum of x times p of x. So I need to multiply the x times p of x together. So I'm multiplying 0 times this, 1 times that, 2 times that, 3 times that, and 4 times that, and that gives me these answers. Then I want to add those together. So the mean is equal to 3.9598, or 4. So when you check your answers, we usually are going to round that up to 4, but when you do the standard deviation formula, you want to use this original mean, the one that's not rounded up. So the standard deviation, sigma, is the square root of the sum of x squared times p of x minus the square of the mean. So we need to square the original x's, so I get 0, 1, 4, 9, and 16, and I multiply those by these probabilities here, and that gives me these values. Okay, so then I want to find the sum of those. So the sum of the x squared times p of x is 15.7204. Notice I'm being kind of generous with my decimal places because it's a formula within a formula. So you don't want to round this to the nearest tenth. You want to round it to about 4 or 5 decimal places. So 15.7204 minus the mean squared. So notice I went back to that mean that wasn't rounded up. There's that answer. And then this is showing another way to type this in. You can square root the answer. So the standard deviation is going to be about 0.201. So you can type this in your calculator in one step. You do second x squared. That gives you the radical. and then you type 15.7204 minus 3.9598 squared. Hit your x squared button there, and then press equals to get this answer.